keep working on SRAMs. So SRAMs is called static. Why is static? Because they use latches. Dynamic range DRAMs uses transistors and capacitors to store charges, right? And that leaks. So you have to keep refreshing the charges in the capacitor. So that's why it's a dynamic, right? Because keep doing that, okay? Otherwise you'll lose all the data in the capacitor. So in that case, DRAM consume more power because it keep refreshing the data in the capacitors. It's static, right? Static. As long as it holds the value, it's being put up and put down by these VDD and grounds, and it's not consuming a lot of current. It's just leaking a little bit, but it's a strong pull up, a strong pull down. So for the SRAM, it's a latch like this. So why is it called a latch? Yeah, 0, 1, right? And 1, 0. Stable. What if you add another inverter here? Put three inverters in a ring. What's that called?
Ring oscillator.
Yeah, it's gonna oscillate, right? So how this works? When you give a rising edge to the work line, you turn on these transistors and you are able to write and read from the latch. Okay? And this is a static memory over here, it's a little latch. So this is powered up and grounded. So it's able to latch the data in this little ring here, okay? So the way it works is, for example, for the read operation, first step is that you have to load these lines, charge it up, charge. Okay, what's happening is you dump charges, and we know that there are a lot of parasitic capacitance everywhere, right? So here's a signal. 5 knot, for example, that's what we name it. Okay. You give a falling edge to this pin. It's like 2 buckets on the top, right? 2 water reservoirs on the top, and there's a switch at the bottom of the buckets. So turn on the switch to dump water to the bottom really quick, and then shut it off. So like this, right? You give a falling edge, the PMOSes are on, it dumps charges, start dumping charges to whatever over here, the capacitance over here, okay? Capacitors. So there are capacitors in the gate, right? There are some capacitors over there. So the line is gonna store what? It's gonna store a VDD. So pre-charge these 2 lines with the VDD first, okay? And then shut it off. So whatever being stored on the line is called what? It's floating VDD, right? It's a floating VDD. It's not permanent. If you so it holds a finite amount of charges, and the voltage is VDD, and that charges will give you a VDD if you probe it against the ground. So you do that first, okay? Then you send 1 to the word line, then the data will show up. So this one is not being read if you don't need it. So the bit line here is being read. That's the data, right? That's the data when you are reading it. So my question for you guys, think about it. Why do we want to pre-charge it to VDD? What's the reason for that? This will be on the quiz in the future, okay? Why we want to pre-charge the bit line and bit line bar to VDD previously? So let's give an example here. If we had 1 and 0 being held over here at the very beginning, it's possible, right? It's possible. Okay? This is getting put up, this is getting put down. It's an inverter, so it's stable. It's latched over here. As long as I have power applied, it will stay. Okay? 1 and 0 being written as the data. Okay? So now I want to read it. Basically, I want to read this one here. I want to know what was stored over there. Don't worry about this one. It's okay. So if you don't want to read, because this is just the inverse of this guy, right? So this is the data. I want to read this data. Send a rising edge to word line, data will be available. But why we want to pre-charge this line to VDD first?
I guess there is a discharge.
Mm-hmm.
The floating point of floating VDD that's stored in the SRAM.
So if this was 1 and this was a floating VDD at the very beginning, am I reading a 1 here after I turn this on? Am I losing anything? Why no? I want to hear the answer. Since you guys are experienced engineers, electrical engineers, I want to hear the answer. Easy, right? So if a 1 here, which is VDD, right? This is VDD, right? And this was pre-charged to VDD, but this is a floating VDD. I had a floating VDD and a put up VDD. What's the difference, voltage-wise? Huh? No difference. It's just this VDD has a big family supporting this guy, right? This is an immigrant like me, floating in the U.S. No one back me up, right? If I'm gone, I'm gone. Finite amount of whatever. What's the difference? No difference, voltage-wise. So if the voltages on the two sides are the same, is there going to be a current flow? No. If I don't tell you I'm an immigrant, you couldn't tell, right? You don't know if I'm an immigrant. So there won't be any current flowing. It's still VDD. VDD, there's no voltage drop, no current. Am I reading a VDD here? Am I reading a VDD? If I turn this on, am I reading a VDD here? Yes, it's not getting discharged. It's still a VDD. I'm reading a 1. Good. Because it stores the 1. And I'm reading a 1. It's good. Right?
Yeah.
What about this?
That'll drop it. Using the rising edge. Then miss the middle. VDD will go to 0.
Yeah.
And then
What's going to happen? Yeah, so because this is 0, right? It's a strong 0. Connect to this guy or this guy? Which one 0? This 0 shorts to this guy's ground or this guy's ground? The bottom one, because this is output. The output directly has a channel go to the animals, right? So the finite amount of charges here, it's floating VDD, will be drained to the ground here, right? So, and then you are getting a what? 0. Okay, and you turn on this one, it's going to discharge and reading a 0, right? Still good. It's also good. So why do we want to pre-charge this one to VDD? That's my question. So what if I pre-charge it to?
If it was 0, then you would short the. Then you would, if that wasn't charged up to VDD, then when you have a 0 on the inverter, then, or sorry, when you have a 1 on the inverter, then you'd read a 0.
You mean here?
Yeah, if you have a 1 there, and you have a 0 on bit line,
Mm-hmm.
and you read it,
Mm-hmm.
then you'd read 0, or you'd read 0.
You read a 1, right?
Well, it could be.
Wait, what you read from here though? This is on, right? If this is a VDD, this is on.
Mm-hmm.
So it's on, right? Because VDD minus 0 is larger than V threshold. Okay? So 1 will go here, right?
Yeah.
We're still reading a 1 because the data is 1. Why not? Still a 1.
Oh, but you're losing. You have a current, or you're draining power.
Yeah, but it's
So
not a.
Maybe that's not ideal. Maybe it works, but it's not ideal.
So is almost good at passing ones.
No.
That's why. So which are reading here?
You're reading an unclear one.
No.
So you're reading a 1, but like, it's just you're wasting power.
It's part of it, but you know, if you have a VDD, you're also wasting power of the pre-charged VDD, right? Every time you pre-charge, you're also consuming power. If you pre-charge it to 0, actually, you just ground it. You just dissipate whatever like residue charges on it, right? So power is probably not that significant difference, because if this is if you ground it, you know, and then shut it off, it's the floating ground, and then you had a 1 here, it will charge up this point and put it up to 1, start reading a 1. My question is, can you really charge this up to 1? We learned it in the past. We covered this a lot, huh?
No, it'll be 1 minus.
Yeah, it will be 1 minus VTHM. So you are losing a voltage. And sometimes it could be very significant because for low voltage, low VDD, low power design, it's only 1 volt, and it's going to be 1 minus like 0.3 volts. You're only reading 0.7 volts. It could be a problem. Okay, so that is why we want to pre-charge to VDD. Okay, this is how we read it from there. That's how we read it from there. Keep in mind, even though we don't have homework assignment, because you guys have a lot of cadence assignments, so I haven't assigning any homework from this class for a long time. You want to have like a homework 4 9 weeks ago, then that's it, right? But you have a lot of labs. Study this, there will be a quiz at the moment, okay? So this is for reading. How do we write it? How do we write? So you need a certain circuit to write it. But so for this is just 1 cell, right? It's 1 cell.
Yeah.
Could we? How do we expand it?
For writing.
Yeah, for more bits, right? Like 8 bits, a byte. If it's a byte, I'm gonna store a byte of data in here. How do we expand it? Just have another module on the right? You just extend this word line. Whenever this word line hits this port, it's gonna turn on all the bytes in the line, so you can read and write for the bytes at the same time. It's doing 8 bits, right? At the same time. It's just 1 cell. So 1 cell. That's for SRAM. So reading and writing requires a little bit more circuitry over there. Okay, so that's the right signal. It's active 1. It's active 1.
Is it going to both of those?
Yeah, both gates at the same time. And this signal, we call it data underscore S1, data signal 1, right? And this is the bit line, this is bit bar. All right. So if I have a 0, 1, pre-stored, and I want to write a, I want to write a 1. Give me a second. So the write signal, yeah, let's just analyze all the cases. It's pretty simple. Okay. If I want to write a 1, for example, we give us this data. Let's put a table here. Okay. If this is 0, what's going to happen? If this is 0, and we had this is just a signal line, right? We give us rising edge, will trigger the write command. Okay, we'll trigger the write command. The same thing. If you have a word line, a rising edge, so this cell and all the following ones are getting selected, right? So you're going to write into it. If we put a 0 here, and we had 0 and 1 previously stored over here, what's going to happen? Let's just look at that, okay? 0, 1, right? And this will be on. This will be on. And if the write command comes up, the rising edge, this will be on as well. And this was pre-charged to VDD. Pre-charged to VDD. And here's the 1 here, and this is on. This is a pre-charge. So the pre-charged VDD is actually not doing anything because you can drain the residue charge to ground easily. It's just nothing back it up, right? So you can drain it easily. But what about this one? It's being backed up by this guy, right? It's going up. So if you are doing, if we call this Q1, this is Q1 bar, okay? That's the data, okay? The data. Are you flipping the signal? Are you flipping the data here? If you're doing this, if I give a 0 to it, what's happening? So this channel is on, okay? And this VDD can be discharged easily, and you still have a solid 1 here. What's going to happen? So think about the latch. So what is the latch is doing? You have to have that kind of model in your mind. The gain of the latch is actually really high because of the inverter, right? So 1 is 0, 1 is 1. If this is 1, is 0. And whenever the signal on one side got changed, getting very close to 2.5 volts or to the threshold voltage, to the switching point, it'll flip really quickly. Can you imagine that? Because the inverter, right? It's an inverter. If you got, for example, this one starts dropping to 1, let's say 5 volts, okay? So it starts dropping from 5 volts because you turn this on, start draining charges to ground, and this one starts dropping. Even though you are thinking, hey, it's shorting power supply to ground. It is, right? It is. So this is, you have to design, so it's a side question. So in order to, compete with this VDD, what you need to do over here? They are both on, right?
Yeah.
But however you want to flip it, what's the design consideration over here? They are both on. VD seems like it's shorted to ground, but actually it's not because there are also like channel resistance over there, but it's very close, right? Very close. However, it's competing, right? Competing. It all happens really quickly, so we don't have to worry about the power consumption over here.
Do you get a voltage drop then?
I mean, no, the design consideration to make this happen. So this has to be weak, right? The PMOS here has to be weak.
Yeah.
And you need the super fat NMOS here. to pull it down. So this will be put down from 5 volts, and then it's getting closer to 2.5 volts, and boom, just passes that switching point, becomes 2.4 volts. What's going to happen?
Then you switch to 0, get inverted, and that will change to 1.
So this will be considered as 0, and this one will be put up to 1 quickly. Keep in mind, that's a super high gain. We'll do this, and it's a positive feedback. This goes up, we'll pull this even down further, and we'll do this, right? Okay? That's what's going to happen. So in that case, if you have a super fat NMOS over here, is we'll pull this down, and this will be discharged, and then we'll do this. Okay? So this becomes what?
It becomes 1.
1. Okay? Remember, what is this operation over here?
Right, so if you just
So if I have a 0 for this point, I'm writing a what to this guy? 1. So I'm writing to this. And then I can have a floating edge to the right. So this is getting shut off. This becomes floating again. So whenever this is getting floated, which transistor dominates?
the rounded.
The latch. The latch dominate. Will give it super strong pull up here, and it's a solid pull up. Start getting a static memory. So if this is 1, what's gonna happen? This is 1.
So
1, 0. Right, this is off, right?
And what's the
And this is
data set
1. Huh?
to? What's the data set to?
0, 1. This is 1. This is on. It's getting put down. So only the pre-charged VD is getting put down, right?
yeah.
0 will be passed because the NMOS is good at passing zeros. So you're writing a 0 to it. You're writing a 0 to it. It was 0. You're not doing anything.
Yeah.
It's okay. It retains a 0 value over here, right?
Mm-hmm.
So still the same. Still the so you're writing a 0 here, but still the same. It's still 1 here. But what if we had a 1, 0? It should be very simple to analyze, right? Just based on the previous one. So if
You want stronger inverse.
you want a stronger most here as well, you're gonna write a 0 to it. So here's the data. That makes sense, right? That makes sense. You may need an inverter because it's getting inverted.
Yeah.
So here's the data. Okay? Being written to the SRAM. So this is everything about SRAM that you need to know. We're not running simulations, not doing layouts, but there will be a state diagram for this guy. How to do a layout of it. This will be very repetitive. Imagine the SRAM could be 24 kilobytes. It's a lot. It's a lot. Divided by 24 kilo, right? Every byte is 8 cells, right? 24 kilo, you have 24 kilo over there. It's pretty long.
That's huge.
So it's very repetitive. That's why for each design, it needs to be optimized, right? If every single one is saving a little bit footprint, you are saving a lot eventually. So that's important. Another thing is for the SoCs, microcontrollers, you are looking at the memory, like all the buffers we're talking about, right? The buffers are all SRAMs, right? So are all SRAMs. So the microcontroller, you store something in a buffer bracket like 20, 24, 32. So these are actually SRAMs being deployed, being used from the C code, right? So you need SRAMs, a certain amount of SRAMs. That's critical, I can tell you, and that's why we switched from Arduino Uno chip, which is only $1, $2, and it's a DIP microcontroller, can be easily soldered and tested on the PCB, and that was a Skyboard version 1. And just 2 weeks before the semester got started, we found out when we were approaching lab number 8, we found out it's not going to work for lab number 8. because it doesn't have enough memory. And when we are recording an audio signal to the chip, and we are trying to read it out page by page for the SD card, which is 512 bytes, and it won't be able to handle it. So the Arduino Uno chip, $2, so easy to solder, so cheap, $1, $2, just doesn't work for our application. So 2 weeks before the microcontroller class, we switched to the mega chip, $17 per chip, and super difficult to solder, and we just have to do it. So in that case, you know that the amount of the size of the RAM is critical. So we are looking at microcontrollers. If you look at the size of the memory, we'll probably give you different prices, different cost. Okay, you always want to have a balance between the size of the memory and your application and the cost. So if you're doing SD card writing and reading, you probably need a bigger RAM because SD card requires 512 bytes to be read and written at the same time. So you need a bigger memory for the buffer. So for microcontroller design in the future, you could, so this latch can be replaced by DP flops. So how many transistors are in here? Just for this one cell, not including these ones. 6. So this is a super popular structure. It's called a 6-cell SRAM. I mean, could be in the interview, could be anywhere else. If you are looking at SRAMs, you probably can see a 6-cell SRAM, so you know what's happening. The 6-cell SRAMs is talking about this guy, okay? And it's being optimized because this circuit cannot be synthesized by your Verilog, by your digital description language. You are going to, if you haven't taken that, it will be covered in 433 in the spring. All right, and if you describe a latch in that digital signal, the digital design description language, Verilog, it won't synthesize the SRAM for you. This is designed by human hand, right? And IPGA doesn't have these latches in IPGAs. Or if you write it in Verilog, it won't be able to synthesize this kind of 6-cell thing for you. So if you write a Verilog, write a description language, and synthesized, eventually it becomes a DP flop. How many cells are in DP flops? You can imagine. We know there are NAND gates and everything. It's a lot of transistors, but definitely not 6. It should be way more than 6. Okay. So in that case, if you are designing a microcontroller and you are not using a memory compiler, which is a specific software being provided by the foundry, it's a software running on the server in Linux or some other kind of machines. You just describe the memory by the behavior in Verilog, you synthesize it. Eventually, it's going to give you different flops based on latches or SRAMs. And that will be huge. Remember the one I showed you last time? The memory banks I showed you on the chip on Wednesday, right? So the chip from Cadence, you have 2 memory banks, really long. And these are already a lot of memory over there. And you can see it takes a lot of space. And these ones were actually designed by the memory compiler from the foundry. If you want to implement the same size of the memory using Verilog and just simply synthesize it using DP flop, it's probably going to be 20 times more larger than that. Okay, and your chip won't be able to fit this much of memory over there. So the conclusion is that you synthesize your digital design using Verilog and certain tools, but the memory has to be designed and compiled by a different tool. Okay, and that tool is called a memory compiler. And the memory compiler is going to use a different library which have all these SRAM cells. Okay, you compile it, and it will generate a netlist or digital circuit using these certain SRAM cells, which were optimized by the foundry, because the foundry, like TSMC or other places, they already designed the schematic, the layouts for you, which are optimized, because these are repetitive structures which has to be optimized, and they know it works. It's giving you great yield, right? So you have to use a memory compiler to design that, and then place it in your design as your RAMs. All right. So this is SRAM. DRAM was simple. I showed you guys just transistor and capacitor, right? There are some decoding structures and everything you need to know. But that's it. We are not covering anything else of the DRAM. So for another thing, let's go flash, right? Flash. Like I told you guys, these are sometimes also being referred as EEPROM, right? EEPROM. So ROM is a read-only memory. It's a read-only memory. Decoder. This. It's a circuit pre-designed by the circuit designer. You cannot program it because it's read-only. So this circuit is already built into a chip. So if you read from these points, I probably need one more here. Decoder. Okay, so connections are only at the gates. Okay. This kind of circuit is already built in the chip, right? So if you are reading these ones, this is bit 2, bit 1, bit 0. What kind of data you are reading from here? What data you are reading from here? These are NMOSes, all NMOSes. Strong NMOSes.
Yeah. So it would be
Oh. Nothing. No NMOS here. Just make it different for you guys.
we mean what kind of bit, like a
So decoder will select each row individually, each row a time, right? So for example, this is
yeah.
what is being selected. The decoder is outputting 100 at the moment. What's the data being read over here?
In red it would be it's just 1, 0, 0.
0, 1, 0. Because these are strong NMOSes.
So it's
0 because this here is grounded, even though this is open. You can disable the reading by giving a 1 here, but now we are reading it, so ground give a 0 here. So these are all on from VDD. And I think you can control this pin here, but doesn't matter. These are strong NMOSes. So if you select the first row, oh sorry, 1, 1. Right? This is not selected. That's why it's not showing to ground over here. Does that make sense? So this is grounded, and there's nothing here, and there's nothing here. So they both put up. So you're getting a 0, 1, 1. Okay? Similar concept. If you have a 0, 1, 0, what's going to happen? What's the data being read over here?
it'd be 1, 0, 1.
Huh?
It'd be 1, 0, 1, correct? Because it'd be
No, this guy. This row is selected.
oh, it'd be 0, 1, 0.
Yeah, 0, 1, 0. Okay, there's no NMOS on this line, so it's put up, right? And this is put down. Wait. 1, 1, 0, sorry, 1, 1, 0. Because this line is not selected. So this NMOS is not applied to this data line. So this line, it's gonna be 1, 1, 0, right? Can I write to it? Can I write to it? This memory. Can I write to it?
No.
No, it's read only. You cannot write to it. These are already designed. It's placed. It's physically connected. So this could be used as a bootloader circuit for the microcontroller, and whenever the microcontroller is getting powered up, this data will be automatically read into the CPU as a preloading some kind of code or data into it to start things up. It's quite useful, but it's a read-only. Cannot change. Can never change it. So for flash, it's something you can change, and the way to program the flash is using something called floating gate. It's actually using floating gate. Using two layers of poly. I just showing the concept over here, okay? So what's happening is when you apply 25 volts to P2, the electrons in here in the substrate will be forced into P1. It's very interesting, in fact. Because the voltage is too high, right? Voltage is too high, too strong. And so the electrons will escape from the substrate and being trapped into here, right? You give a high voltage, then you disconnect it, and the charge will stay. Okay?
Yes.
And if you give a, let me see how to discharge it. So when you discharge it, you have two gates. I don't want to drill the well, make it complicated. So what you do is you put a high voltage here and you ground the gate P2, and the electrons pre-charged in the P1 will get out from this one and being attracted to the anode of the power supply because high voltage is able to do it, right? So, and then it will even go further and turn the floating gate to positively charged, right, to plus. So that's the different charges to be stored in the floating gate for different data, okay, so for different data. So, and that charge being trapped in P1 will stay for decades. And that's why your solid state drives and USB thumb drives is able to store data even it's not being powered up, because the trapped charges will stay there for a long time. And that's a flash. You can write and read from these data units. So flash is more modern, and you can read and write to it, but can tell it's more expensive because these ones are special structures. It's larger in size. And why larger in size? Because you are applying a big voltage. The big voltage requires a larger size, otherwise it will be burned, right? So that it will be damaged. So it's able to handle the larger voltage, so that's why it's big. It's large transistors, and also requires the voltage higher than regular VDDs. Right, VDDs is usually 5 volts to the USB. So what's the technique you can use to bump the voltage, to boost the voltage, to charge pumps? So USB thumb drives have charge pumps to boost the voltage to 225 volts in order to do this, write and read. All right, that's it for today.